everyone. Welcome back to Learning at 11th Hour. Today we're going to look at Norton's theorem. So in the last video, we've already discussed about Thevenin's theorem. Now, having a close look at it, we would realize that it is just a simple source transformation if you want to obtain the Norton's equivalent circuit from the Thevenin circuit. So let's look at what it is in detail. So if we have a linear active bilateral network, it can be replaced at any two of its terminals by an equivalent current source in series with an equivalent resistance, whereby the current source would be called the Norton's current source and the resistance in this case would be the Norton's resistance. So as this diagram shows, we see that if there is a linear active network with a load connected to it across AB, it can be transformed into a current source, equivalent current source with an equivalent resistance in parallel with the current source. And this entire setup is connected across the output terminals AB where the load resistance would be connected. So in order to arrive at this Norton's equivalent circuit, these are the steps which we need to follow. So the first step is very similar to the Thevenin's theorem, where we need to identify the output terminals and we need to remove the load resistance. But instead of open circuiting, we are going to short circuit the terminals across which the load was connected. After this, we need to compute the current, the short circuit current, which is flowing through that terminals, which is shorted right now. Then we need to kill the sources. So if it's a voltage source, we need to short it. A current source will be opened. And we need to compute the resistance looking in from the output terminals. So this step is also similar to the Thevenin's theorem where we find RTH. In this case, it will be called RN, the Norton's resistance. So once we obtain the values of IN and RN, we can draw the Norton's equivalent circuit. Then we can compute the load current. So if we observe this circuit, if there were to be a resistance, load resistance connected across the terminal AB in this manner, then R dash and RL are actually in parallel. So I dash is the total current, which will split up maybe as I1 and I2 here, where I2 is going to be my load current. So in order to compute the load current, I can use the current division rule. So that is what this formula says. The load current is the opposite resistance by sum of resistances into the total current. Because here the opposite resistance is nothing but R dash. In my case, it's going to be Rn. Sum of resistances Rn plus RL. So we get Rn by Rn plus RL into the total current entering the two branches, which is IN. So that is my Norton's current. So this is nothing but the current through the other branch, RL branch, which in turn becomes IL. Let us now look at an example where we try to obtain the Norton's equivalent circuit and compute the load current I through the 10 ohm resistor. This is the same example that we took to apply the Thevenin's theorem. So let's begin. The first step is to identify the output terminals. So this was the output terminals and the resistor 10 ohms was connected across it. I have removed it now and I have to short it. The next step is to obtain the current ISC, which will be equal to IN flowing through this AB. So we can do that by applying mesh analysis. So if this is I1 and this is I2 assumed in the clockwise direction, I can apply KVL to loop 1 and loop 2. So KVL at loop 1 will be obtained as, let me mark the directions, plus minus because of I1, I2 will be in this direction, so plus minus. So these are the drops in the 6 ohm resistor. This is the drop direction for the 4 ohms, 10 ohms and 10 volts and 12 volts. So applying KVL at loop 1, what I get here is minus 10 plus 4I1 plus 6 I1 minus I2 because the two directions are opposing each other plus 12 is equal to 0. So then we get 10I1 minus 6I2 is equal to minus 2. Or I can say 5I1 minus 3I2 is minus 1. So this is my first equation. Now applying KVL at loop 2, what I get now here is uh, 6I2 minus I1, because right now we are analyzing the second loop. So we consider that the direction of I2 is the predominant one, and therefore I1 is opposing it. So I2's direction is positive, I1 is negative, and followed by minus 12. This is equal to 0. So I2 minus I1 is equal to 12 by 6, which is 2. So now we've got the second equation over here. So when we solve this, what we get here is we can obtain the values of I1 to be 2.5 amps and I2 is obtained as 4.5 amps on solving the two simultaneous equations. After this, we need to compute. So here our I2 is nothing but the short circuit current ISC, because the current I2 that we've assumed in this loop and ISC are one and the same. So I can actually say that ISC, or the Norton's current source's value, is going to be equal to 4.5 amps. Next, we need to compute the value of Rn, which is going to be the same as RTH. So here we need to kill the sources and find the resistance looking in from the terminals AB. And in this case, we have to remove this short circuit and then consider the equivalent resistance looking in from RAB. So what we obtain now is a circuit like this. So we have a resistor over here. We have a resistor over here. So this is say 4 and 6 ohms. And these are the terminals AB. This was shorted. Now I remove the short circuit and then I have to compute RAB looking in from AB, terminal AB. So then RAB becomes what? 6 and 4 are in parallel with each other. So RAB is nothing but 6 into 4 by 6 plus 4, which results in the value of 24 by 10 ohms, which is 2.4 ohms. So now we have obtained the value of Rn as 2.4 ohms and In as 4.5 amps. We can now construct the Norton's equivalent circuit. So we are going to replace this entire network with the sources as one current source, In, whose value is 4.5 amps, with the Norton's resistance in parallel with it, whose value is 2.4 ohms. We now can reconnect our load, which is 10 ohms, and we've been asked to compute the value of IL. So now this 10 ohms resistance and 2.4 ohms resistance, both of them are in parallel with each other, and there is a current source connected to it. So we can apply current division rule to it. So when we go for current division rule, the formula says IL will be equal to opposite resistance 2.4 divided by sum of resistances. So 2.4 plus 10 into the total current entering the two branches. So that is into 4.5. So this turns out to be 10.8 divided by 12.4, which again becomes 0.871 amps. So this is exactly the value that we have arrived at for the Thevenin's circuit also. Now, if I want to obtain the Thevenin circuit from this, so this is basically a current source with the Norton's resistance in parallel with it. So I can transform this current source into a voltage source to obtain my Thevenin circuit. So what would the value of the voltage source now be? So the arrow would be pointing the positive. So this will become VTH. So that would be nothing but IN into RN. That is going to be the value of VTH. So we'll get 10.8 volts This will be in series with RTH, which is nothing but Rn, so 2.4 ohms. And then we have our 10 ohms load. So this is nothing but the Thevenin's equivalent circuit. Whereas this one that we have obtained with the current source is the Norton's equivalent circuit. So the two are nothing but a source transformation away from each other. So that's all with today's video. I hope you've understood the concept of Norton's theorem and how you can simply obtain the Norton's equivalent circuit by performing source transformation of the Thevenin's equivalent circuit. Thanks for watching. Please keep watching the videos for gaining knowledge about circuit theory. Do subscribe to this channel. Bye bye.